second talk. But Jordan Ellenberg from University of Wisconsin will give a talk with a very long title.
Well, thanks, and thanks to the organizers for bringing me here. It's my first visit to the Newton Institute, which is a terrific place to have a conference. So as I said, I gave a kind of all-inclusive title, and I think I will try to say at least something about all of the elements of the title today. Let me start. Well, the first thing I want to say, of course, is that the work I'm going to talk about today is, well, all of it is joint with Akshay Venkatesh, and some of it is joint with Craig Westerland, and some of it is joint with Nigel Boston. So these are the collaborators on this project. And what I want to start with is I just want to write up on the board 4 questions of what you might call statistical arithmetic, 4 statistical questions about the arithmetic of global fields, which I'm going to arrange in kind of what I take to be roughly increasing order of difficulty. So here they are. So the 4 questions. So one, here's an easy one. What is the probability that a random positive integer is square free? And by the way, by random, I'm always going to mean maybe I take my integer in a dyadic range, x through 2x, and let x grow. So implicit in these questions is the idea that under this process there is some limit. Even that is, in general, not obvious. For this question, of course, we know the answer. It's 6 over pi squared, the inverse of a special value of a zeta function. Let me move up here and write more questions. So question 2, I'll phrase this in a slightly unusual way. What is the expected number of surjections from the class group of K to Z mod LZ, or dually I could ask about the size of the L torsion in this group, where K is a random quadratic imaginary field, where again I mean this means a field with discriminant between x and 2x for some large x. And one asks whether there's a limit and what it is.
But is L fixed then?
For a fixed L, that's right. So this, a priori, this question could have a different answer for every L. And I'll come back and sort of say what we expect the answers to be for each of these after I write the questions. So question 3. What is the probability that there does not exist a totally real quintic, and I'll write S5 extension, meaning that the Galois group is the full S5 when I pass to the splitting field, of Q with discriminant capital N, where N is a random square-free integer. So all these questions, by the way, you'll see are really about algebraic number theory, are about extensions of global fields. And here's the 4th question. What is the probability that there exists an infinite Pro2 extension of Q ramified only at P and Q, where P and Q are random primes, each congruent to 5 mod 8. And the point of choosing this particular setup, 2 primes congruent to 5 mod 8, is just to put ourselves in a situation where we don't, where the maximal Pro2 extension unramified there might, as far as we know, be finite, and might, as far as we know, be infinite. There's no Golod-Shafarevich reason to know that it's infinite by force. So what I want to talk about today is kind of if you like, a machine for making reasonably principled conjectures about questions like this, and to give some idea about how you can prove results towards these theorems in the case where the global field is a rational function field over a finite field. So I don't want to oversell this talk. I certainly am not going to say anything about how one might prove the conjectures I'm going to make over a number field, because I don't know. But I will say something. I guess part of what I think makes these conjectures principled is that there's a route to proving these conjectures or results towards them over global function fields. So maybe just to whet your appetite, I'll sort of say what the answers to these questions are supposed to be, and that will give some hint as to sort of what the conjectures are going to look like in some of these cases. For conjecture 2, questions like this are the province actually not of our conjectures, but of an already rather popular and highly numerically estimated set of conjectures, the Cohen-Lenstra heuristics on the variation of class groups. And so in particular, the answer to this question is supposed to be 1. For all L, to answer John's question, whatever L is, the answer to this question is supposed to be 1. And this is actually the only one of the latter 3 questions in which there exists any theorem in the number field case, namely the theorem of Davenport and Heilbronn, which is that this is in fact the case when L equals 3, where the problem is essentially counting Z mod 3 Z extensions of a quadratic imaginary field is very close to the problem of counting cubic fields of a given discriminant, and that's what Davenport and Heilbronn did. So here's almost the one fact about number fields I'll say in this talk. So for question 3, I'm gonna try to make an argument that you should believe that the answer to this question is e to the minus 120, e to the minus 1 over 120. That's a number. Maybe I'll just point out that that number is pretty close to 1. So in other words, quintic extensions are fairly sparse in discriminant. And for question 4, I'm going to make an even more tentative suggestion that the answer to this question should be 1 in 16. So those are the proposed answers, and I will try to now talk about how some kind of notion of equidistribution that generalizes to a more non-abelian setting, the very popular use of random matrices to make conjectures in more abelian parts of number theory, leads us to give answers like this to these questions. So that's where the non-abelian stuff will come in. But in order to explain this, I'm afraid I have to sort of pollute this workshop with a little bit of abelianness. Just to remind you of sort of the Cohen-Lenstra conjectures and where they come from. Otherwise, I think what I say won't make sense. So let me start by recalling the Cohen-Lenstra conjectures and how they can be formulated in terms of random matrices.
Question 4, do you allow ramification at infinity?
Yes, we do. Yeah, this is the part where it's easiest to gather data in the Pro 2 case, and then the infinity is more complicated in that case. I mean, Pro P is a little easier for P odd, but I'll state it like this because this is where we have some data. Okay, so let me start by talking about random matrices and Cohen-Lenstra. And this is sort of a concerning question. This concerns questions like question 2. If we think of this over a function field, so let's replace Q with FQ parentheses T, and let's have Q not have characteristic 2 or L. So I'll try to remember to always say this, but let me emphasize that every single thing I say in this talk is going to be tame, and if I ever forget to make the characteristic of the field prime to everything, then I just forgot, but I really do mean to. I think there's really, really interesting questions if you drop that, but for today, everything is tame. So then the question of what is the L part of the class group of a random quadratic imaginary extension transforms into a question about the L part of the FQ rational points in the Jacobian of a random hyperelliptic curve. So let me rephrase this question, how this question looks in the function field case. So then we are asking, what does, if I take the Jacobian of this curve x, I look at the FQ rational points, and I look at those points that are killed by L. So here's some elementary abelian L group. What does this look like when x is a random hyperelliptic curve over FQ? And now random means randomly chosen on the set of FQ hyperelliptic curves of some genus G, where G is getting large. Yeah.
But here you're only taking imaginary field, right? So what's the?
So this would correspond to, so this is always sort of a sticky wicket when, I don't actually know what that means, but I'm in England, so I thought I should say it. In this kind of thing. So in order to make the analogies, you usually have to take your global function field and sort of choose one point willy-nilly and call it infinity and sort of impose a condition there, whether it's that it's totally split or, so quadratic imaginary, for people who do this kind of thing on function fields, they would say, oh, a quadratic imaginary hyperelliptic curve is one that's ramified over this point that I've specified as the point at infinity. But actually, I mean, I can phrase this question, for the heuristic I'm about to give, I don't have to say it. When I say something more precise, I'll say it.
I guess I could have gone back to ask for the real case, you don't say anything.
So for the real case, you get a different answer. I think you get 1 over L. And the reason is, the problem is that the class group of a real quadratic field really isn't analogous to the L torsion and the Jacobian of a hyperelliptic curve, because you're really sort of deleting 2 places in the real quadratic field, the 2 real places. So what that's more like is something somewhat more complicated, which is you take the Jacobian of the hyperelliptic curve and then mod out by the image of a random rational point. And then you get some group which is typically much smaller. And then every time I said sort of symplectic group, I would say extension of symplectic group by ZL or something like this. So, so that's why if you look at these Cohen-Lenstra papers, you see that the quadratic imaginary case is always much the simplest, and that's because it's the one that's really truly analogous to Jacobians. So there's a lot that I could say more generally, and I'm trying to say in the simplest possible case for the sake of exposition.
Are you asking for a number or for a group?
Well, yes, you should think of this. You should think of this as a random variable taking values in elementary abelian L groups. So you could think of that as the isomorphism classes are just given by a number, their dimension. Now, what you should be saying is, oh, do you mean in the set of integers or in the category of? That's what you should be saying. So hold that thought. Whether, I mean, it's a random variable that. Actually, forget I said that. I'll say it later in a way that makes sense. I tried to say something that I'm going to say later, but I'll say it later. Anyway, so what might this look like? And now here's our kind of leap of faith. I mean, let me point out that you can describe this as, well, let's call this A. So this is our random variable, which takes values in elementary abelian L groups. So you can write A as just the, if you like, just the co-kernel of Frobenius acting as a linear transformation of the Tate module of the Jacobian. And now here's the leap of faith that we make when we leave the realm of things we can prove and go into heuristics. We say, well, we don't really know anything about how Frobenius acts, except that it acts symplectically. So let's suppose it's a random symplectic matrix. Suppose prob Q is random, in Haar measure. Well, I should write symplectic oughts of TLJ, but let me just write in SPGGZL. Ah, sorry. Absolutely, that's important. So, sorry, the co-kernel of Frobenius minus 1. And I should write, so to be precise, what I should write is, of course, Frobenius doesn't sit in the symplectic group, it sits in the generalized symplectic group. And I'm going to write a little Q up here, and this denotes the, this is a coset of the symplectic group, and it's the one that multiplies the symplectic form by Q, because we know that's what Frobenius does to the Weil parent. So, but this is still some L-adic space, which has the uniform distribution. And then if we do this, one can it's a little painful, but one can compute what group you get. So from this, you get, so then can compute for each, for each elementary abelian L group A0, what you might call probability sub G that A equals A0. And this will depend on G, right? So for instance, if you ask the probability that it's Z mod LZ to the 1 million, then for small g, that probability is going to be 0. But the miracle is that if you fix A0 and let G grow, and that's the situation we're in, right? Our random hyperelliptic curve is supposed to be a random curve of large genus, then these probabilities actually approach a limit. So this is sort of, in some sense, like the underlying wonderful fact. That's why there's such a subject as random matrices. You don't have to say how big the matrix is. You can just say a large matrix. So limit as, as g goes to infinity of this probability exists and equals what you might call CL of A0, the Cohen-Lenstra prediction for how likely it is that this will be the group. And it's a very enjoyable piece of random matrix theory to actually compute these limits. So for example, if you can compute this limit for the trivial group. So you can say, what's the probability that a random matrix in this coset will have the property that if you subtract 1, you still get an invertible matrix? And that turns out to be the infinite product, 1 minus 1 over L, 1 minus 1 over L squared, et cetera, et cetera. So this, for instance, is the Cohen-Lenstra prediction of what's the probability that the class group will be prime to L. And you can see it's sort of slightly less likely than that a random number will be prime to L, which would be 1 minus 1 over L. It's sort of that to first order, but then there's these modified terms. So I think actually an original part of the making of this conjecture was people noticed that class groups had order prime to 3 somehow less often than you might expect. Less often than 2/3 of the time. And so by the way, I should say that this is not the way that Cohen-Lenstra originally framed their conjecture. I hope I'll be able to come back to the end to their original framing. This was, I think, first appears to my knowledge in a paper of Friedman and Washington. Although somehow they do this for GL, and then this was later corrected by Jeff Actor that this is the appropriate group. And then the happy accident is that whether you take a random element in GL or a random element in this coset of GSP2G, you actually get the same heuristics. It's sort of a marvel. If you do it in SP, by the way, you get different heuristics. So if Q is, I'm sort of implicitly presuming here, if Q were to actually be 1 mod L, things would be a little bit different. So I'm trying to, I should have said that I'm sort of implicitly having that Q generates FL star for this discussion. OK, so.
May I ask a question?
Yeah.
I mean, the probability is not really random. We have the Riemann hypothesis for the eigenvectors.
That's right.
So?
Well, there's lots of reasons that Frobenius is not really random. I mean, so this is a highly. I mean, what can we say about this? I should emphasize that in one sense, if you allow Q to grow with G being fixed, then this is really a theorem, right? You sort of have, I mean, then we know equidistribution in the symplectic group, where Q is getting larger and larger. You're taking larger and larger extensions of FQ. That's not what we're doing. We're fixing Q and letting this group grow. And so we're saying something which I actually don't even have a precise way to phrase what it means for a sequence of elements in larger and larger groups to be equidistributed.
Excuse me, sorry. So if you fix a genus G or a degree or something, it's true that when you go over those hyperelliptic curves and let Q get large, it's still equidistributed?
Yes, that's true. And by Deligne's theorems, you can get very sharp bounds on. So this is sort of this is sort of what Katz-Sarnak is all about in some sense. This fact that you can actually.
So that the monodromy is big enough.
Right,
just
so
for
it is big enough, I guess.
Yeah, so there is a real geometric fact here, the fact that the monodromy in this family is big enough. So hopefully I'll come back to that too. So it's not 100% by pure thought. There is geometry there, but the point is that's a theorem. Whereas what I'm saying is not only not a theorem, I mean, there's no sort of properly phrased equidistribution statement. Nonetheless, you can sort of squint and pretend there's a statement, and then you get a precise conjecture, which is highly numerically verified and appears to be true. And I'll even say in a second, new results that we can prove towards this conjecture. So let me break down. We're still abelian for another like 10 minutes or so. Let me kind of describe how you might attack a conjecture like this in the function field case. So what I'm going to do is the following. So let me say this is the next section, stable cohomology and Cohen-Lenstra over the rational function field. Okay. So let me write HGLR. So this is going to be a moduli space over the finite field. It's going to be the space of pairs PT, where P is just going to be a square-free polynomial, degree 2g plus 1. So Min-Young, the fact that this is odd degree is what's making a quadratic imaginary. When I take the square root of this, I'm going to get something ramified at infinity. And then T is a surjection from the Jacobian of x, the f rational points of the Jacobian of x to, actually let me put in another parameter. I'm going to write z mod lz to the r. So the case I described over there is r equals 1. I'm going to look at, so this is something which is keeping track of what is the L primary part of this group of rational points. So this is some kind of moduli space of hyperelliptic curves with level structure. That's how you should think of it. And I'm also going to write conf 2g plus 1, this stands for configuration space, equals space of square-free P of degree 2g plus 1. So if you like, this configuration space is sort of a map of, is a sort of a space of hyperelliptic curves. Oh, is it invisible when I write here? I'm sorry, I see some people craning.
So you mean the L division part of that group? Yeah? No, it's not just that.
So I mean, it's yeah. I mean, I could also, it would be the same if I just looked at the rational L torsion, and then I'm looking at. So this is just some set which is going to be like a Grassmannian depending on the dimension of this space as FL vector space.
You don't want P to be mod.
Yes, and as always, and the very first time I already forgot to say it, I want Q prime to 2 and L for sure.
But the polynomial P, you don't want the top coefficient to be 1?
I think for what I'm going to say, let's make it 1 actually. I think for what I'm going to say, it should not matter, but let's but no, I do want to actually, yes, let's make it 1. So that that's a
Stupid question.
Yeah.
What do you mean by space? So what is the topology, or what do you mean? Is this head off and
so I can, so I guess what I'm really writing are the FQ points of this space. So what I should, so if you like, I could make this, it's a cover of configuration space. I mean, the configuration space is it's just some symmetric power of the affine line with the diagonals removed. So it's the space of 2g plus 1 tuples of distinct points. So yes, I was a bit sloppy. I should say this is, what I described here is the FQ rational points of the space. So let me just phrase what the Cohen-Lenstra prediction says in another way. Because from the probability distribution on what you expect the L torsion and the Jacobian to be, you can guess what you expect sort of the expected value of this, of the number of points here to be. And another way to rephrase Cohen-Lenstra, so Cohen-Lenstra rephrased, is that if I look at the number of points on this space, and then I divide by the number of square-free polynomials, so in other words, I'm saying, given a hyperelliptic curve like this, how many surjections do I expect the L torsion and the Jacobian to have to z mod lz to the r? And then, of course, as always, I take a limit in G. this is supposed to be 1. So again, I'm rephrasing that conjecture 2 above in the function field case, and it says something like this. And now you can ask yourself, why should this be true? This was actually sort of where we started with this problem. To be honest, we were a little doubtful about whether we really believed this conjecture when we sort of wrote it down. I mean, this is a very strong statement. I mean, these are some sort of crazy moduli spaces that are growing in dimension. Why should these two spaces, why should their fate be so tightly tied together in terms of the number of points they have? So I'll try to explain why that could be.
Now for this H, this is not really a set of FU bound of any variety, or I don't understand.
I think if yeah, it can be made to be, this set is the set of FQ points of a certain moduli space. Yeah.
So what are the FQ bar points of that space?
So that would be, well then the FQ bar points of this space would be monic square V polynomials over FQ bar. But then you would sort of have the fiber over each point would have the same number of, it would be however many maps there are from Z mod LZ to the 2G to Z mod LZ to the R. So this would be this is a finite cover of conf 2G plus 1 with some.
I think then you should rephrase it rather as an injective map from Z modulo and Z to ZR.
Ah, I see. Yeah, I'm sorry. This is, I sort of went, yeah, that is better. Okay. What?
Or else take L torsion
Instead of, yeah, so maybe I should just write it like this, because it's got, in terms of the numerics, it's the same. Yeah, no, that's absolutely better. Sorry. Let me write it. And then injections from, okay, so let me, I mean, yeah, I actually think that's better for this description. So again, the number I'm averaging is the same number, but this is a better way to write it for making it a reasonable moduli space. Okay, so actually maybe now I'll state our theorem. So again, let me emphasize that I'm writing that the Cohen-Lenstra predicted value for this limit, but even the existence of the limit is completely not obvious. So let me state a theorem towards this conjecture.
On the left, is it R equals 1? Or for any, I don't know, is for any R?
For any R, yeah. And I'll Q primed it, yeah. So the statement is that there exists constants, lower bound and upper bound, depending on Q, such that there's a, let's see what's the best way to write this. I guess that this is a lower bound for the lim inf of this quantity. And this is an upper bound for the lim sup of the same quantity. And moreover, that as Q goes to infinity, these approach 1. So it kind of squeezes this thing together as Q goes to infinity. So we show that the number of points in the space does indeed obey a rather strong regularity as the genus grows with Q fixed. So this is actually, although it looks like it the way I phrased it, not a theorem about arithmetic at all. It's a theorem about topology. And so I want to sort of now explain like where the topology comes in. The arithmetic is only sort of at the end in order to translate into a statement about point counting. So Y, maybe I'll say it like this. This is a corollary of what's in some sense the real theorem in this paper, which is that there are constants, a bigger than 0, b, d, such that if I look at the if I look at this space now, look at its complex points as a complex manifold, and look at its rational homology, then what I'm going to say is that this homology stabilizes. And it stabilizes in some range, that is, for I less than something that grows linearly in G. And as I'll say something about, I mean, these spaces, as complex manifolds, they can be defined topologically, and then the proof of this stable cohomology theorem is in some sense analogous to like the theorem of Harrer on the stability of the cohomology of Mg. It's that flavor of theorem, and in some sense the essential topological nugget is the same. It's a theorem about the contractibility of a kind of space of arcs, or I should say a complex of arcs. Okay, now I'm going to say something about why a theorem about the cohomology of these spaces gives you this. Of course, it's via the Lefschetz trace formula, but let me sort of say a little bit more about how this works, and then I'll be ready to kind of non-Abelianize everything. So maybe a good way to see the relevance of stable cohomology to counting points is to actually go back to question 1. I mean, I started at 2, but I actually have in mind now to sort of return to question 1. Why is there a nice formula for the number of square-free integers, or in this case, the number of square-free polynomials? Well, one way to see it is like this. So question, why is there a nice formula for the number of points on this space? If I didn't put square free, by the way, the number of points in the space is pretty easy. It's q to the 2g plus 1. I mean, that's how many polynomials there are. As you suggested correctly, I should say that they're monic, and then there's 2g plus 1 polynomial coefficients, which vary freely. But it's less obvious why there's a formula for how many of them are square free. And one way to see it is the following. So because we know the cohomology of this space, which actually I'll compute on the complex side, as Dali mentioned in his talk yesterday, this is a k pi 1 for the braid group on 2g plus 1 strands. And so the cohomology of the space can be computed by the cohomology of this group. And the cohomology of this group is something that the rational cohomology is something that we've understood for a long time due to Arnold, and is actually quite simple. Namely, well, this is a connected space. And so, by the way, I'm always taking cohomology with rational coefficients. And there's a class in H1. And then that's it. So the Lefschetz trace formula is, for a general variety, pretty hard to apply. But if you're lucky enough to have all the cohomology vanish past the point, it's pretty easy. And you can check that these classes are of Tate type. And when you plug into Lefschetz trace formula, what you find is that so there's certainly something about the comparison of cohomology between complex and étal and characteristic 0, characteristic p that I'm hiding. So sorry for that, but one can do it.
Excuse me, Jordan?
Yeah.
In this theorem, so you're only jumping by d. There's this d.
Yeah, so I think it's probably possible to make that d equal to 1. I guess to make it...
if I recall, in Harer's theorem, you just let g get large or something.
That's right. So this is a technical issue. I think d can be made to be 1, but in terms of if you... but if you want, you can sort of work in arithmetic progressions, and you'll get the same answer. So that's not such a big... I'll just say that that's not a big issue for us anyway. So, and then one gets that the number of points in this space is actually exactly q to the 2g plus 1, that's coming from the h naught, minus q to the 2g. So if you want to write it in terms of probability, it's 1 minus 1 over q times the number of polynomials in all. So this is the same answer in the sense that 6 over pi squared is 1 over zeta 2, where it's the Riemann zeta function, and this is 1 over zeta 2, where it's the zeta function of the affine line over fq, which is the base that we're using here. So here's my kind of stable cohomology answer to question 1. The world's sort of hardest answer to question 1 is because we know the stable cohomology of the braid group. That's sort of the manifestation of why that's a relatively easy question. A stable cohomology for these moduli spaces of hyperelliptic curves with level structure is substantially harder, but now there is such a theorem, and so we're going to get a theorem in the direction of Cohen-Lenstra from that. So let me say, let me now state a conjecture, which I'll then state more generally. So, because of course, just as if you know Harar's theorem, you know that Harar proved that the cohomology of mg stabilized as g grew, but didn't tell you what the stable cohomology was. That came much later. So here we're in a similar position. We know that the cohomology stabilizes, but we don't know what it is. But we have a good guess. Let me tell you what it is. We believe the following, what I'll call a vanishing conjecture, which I'll phrase as follows, that the map from, I mean, this HGLR, you can forget T and just remember P, and as I said, it's a finite cover of configuration space. So the induced map on homology from HGLR, and again, I'll write complex points Q, rational homology, to this space, the k pi 1 for the braid group. We actually believe this is an isomorphism for all I in some linear range. I don't mean to say it's the same range. Maybe I'll write A prime G plus B prime. And then, of course, I call this a vanishing conjecture because we actually know that the cohomology of this space rationally vanishes away from 1. So this is essentially saying that this has no cohomology. But written, I write it this way only to emphasize that what we're saying is that in some linear range, the linear range of terms which dominate in the Lefschetz trace formula, these guys are supposed to have the same cohomology. That said, when you look at this ratio, that's exactly what's saying that this ratio is supposed to approach 1. If these two spaces have essentially the same cohomology in all the terms that matter and make a big contribution to the point count, then that's saying they're asymptotic to one another. So our sort of geometric explanation for what geometric statement would imply a Cohen-Lenstra conjecture is precisely this. And actually, I mean, somehow,
So here, R is fixed and G tends to infinity.
that's right. R is fixed and Q is fixed. That's very important. And then and G goes to infinity. That's right.
So if I was taking R equals 2G, then I would have an action of symplectic mod L acting on the homology. And so can you tell that it's some representation which have nothing to do with having in.
Well, so the problem is if you let R grow with G, I have no sense of what happens. I mean, we have to let, I should say that all these constants, sorry, I should say that all these constants, yeah, this is important actually, are relative to L and R. So that's actually, this is actually important. So that if R grows even rather slowly, and the dependence is really bad, so if R grows even relatively slowly, I can say nothing and I would expect things to be chaotic. Okay. And maybe I'll just remark that in the kind of literature on Cohen-Lenstra over function fields, there's a lot of good theorems actually. But I want to emphasize the difference between letting Q go to infinity and not letting Q go to infinity, because what you can really see from this point of view is that if you ask about the following limit is G goes to infinity, but then I sneakily put in here a limit as Q goes to infinity, the number of points of H GLR FQ over the configuration. Well, now actually the asymptotics become much simpler because, again, thanks to the bounds on cohomology, the behavior of this number as Q goes to infinity is just going to go to Q to its dimension times the number of components. In other words, only the H0 is in there. So the difference between, so this kind of fact, this kind of limit, indeed, Cohen-Lenstra holds in this sense, and that's a known fact, and it amounts to computing an H0. It amounts to computing the connectedness of this space HGLR, which is in turn a statement about monodromy. So maybe I'll just remark that knowledge of connected components, and in Sarnak too, you always see this kind of intervening limit as Q goes to infinity, and it's precisely because what they know about their moduli spaces is some statement about monodromy, some statement about connected components, but not a statement about the cohomology farther down. That's the difference. So knowledge of connected components gives you a kind of large Q, or Q goes to infinity, Cohen-Lenstra. Stabilization of cohomology gives you sort of the existence of lim imps and lim sups, and then actually the computation of cohomology is what would actually give you Cohen-Lenstra.
But don't you also need some bound on the Betty number outside of?
Yeah, you absolutely need that. You have it, but yes, you need that in order to show that the garbage isn't giving you something that outweighs the main term. So you absolutely need that, but one has it. But actually, because of that, and I was just reflecting that I forgot to say something. Because of that, actually, I should say that you actually need this, for this to be the case, you can do it for a fixed Q, but the fixed Q has to be large enough, exactly for this reason that you mentioned. So I should have said this. So for Q, also bigger than some constant, depending on L and R. But fixed. I mean, that's different from having to let Q go to infinity inside the limit. OK. So now I think I've said the last thing that we can prove, and now I'll move on to speculation. And the speculation is always going to be taking a statement like this as what we believe to be true geometrically. But so first let me generalize this a bit, because this is not just a statement about hyperelliptic curves with level structure. Let me just say that more generally, here, I'll pull this down. So I'm afraid that in the interest of time, I'm going to be a little bit vague about the precise definitions of my moduli spaces, because I want to sort of get to some idle speculation. So more generally, let G a finite group, C a conjugacy class in G. Let's even make it a rational conjugacy class, preserved under the raising to Z hat star powers. And then by the Hurwitz space of Gn upper C is going to be the moduli space of G covers of P1. And as always, we're only going to look at this in characteristics prime 2. So everything is over Z adjoin 1 over the order of the group. With n branch points. And now because everything's tame, I can say the tame inertia gives you a conjugacy class in the group G of inertia type C. So this kind of moduli space is much studied. And in fact, we believe that what we say, so the case above, I mean, it seems to be about 1 billion covers of hyperelliptic curves, but of course, the hyperelliptic curve is itself a Z mod 2Z cover of P1. So you can check that the case above is where G is Z mod LZ to the R, semi-direct Z mod 2Z acting as -1 on. So, but in fact, the machinery makes sense for a general G. Unfortunately, we don't have this stabilization theorem for a general G, but one can believe. And in particular, this statement should be true for a general G.
But when you want to apply things to counting, I expect you will need to use mass and not number of objects with some property.
Well, so if usually we think about, I'm not sure if this is the precise issue you're raising, but usually for me, G is going to be a center-free group, and so there's no, or actually, to be completely honest now, this is part of not really, what I'm going to actually do is mark a point over infinity in the cover, and that's going to rigidify away that issue. So actually, that's why if you notice the way I phrased the questions at the beginning, I always said totally real, or I said split at infinity. That's because sort of the spaces that I'm actually going to discuss, I mark a point over infinity. So, okay. So again, we predict this vanishing conjecture that this Hurwitz space, if I give myself a cover of P1 branched at n points, I can just forget the cover and remember the n branch points, the n distinct points. So I have a map from this complex manifold to the configuration space of n points, which again has very little cohomology, and we predict that this is an isomorphism in some linear range now on n. Now n is the variable. So again, capital G is a fixed finite group, and the number of branch points is what's growing. But here I must say, I said this very quickly when we were talking about the hyperelliptic curves because they were always connected. Let me just say, when this Hurwitz space is connected for large n. So it's actually a very nice theorem, if you like a theorem of combinatorial group theory, that the components of this space stabilize as n goes to infinity. And so I think
Why if it's only one conjugacy class and not?
again, for simplicity of exposition, I think a version of this is true, but then you have to use kind of configurations where the points have different colors or something like that to indicate that you have points that you can tell apart under the action of the break group. And because in the applications, but you're right that a full version of this, I mean, you would be able to sort of throw in arbitrarily many arbitrary conjugacy classes, but for simplicity, I'm just saying one.
And in this question, you really want that only this conjugacy class is responsible for all the ramifications.
That's what I want. That's right. So for instance, in the case of, in this case here that we discussed, it would be the conjugacy, there's only one conjugacy class of involutions, and that would be the class. Or in the classical Hurwitz space, like the Hurwitz spaces that Hurwitz studied, it would be the group would be the symmetric group, and the class would be the class of a transposition. That's the simply branched cover. So that was what he cared about most. And that's a case where, I mean, his theorem was that it was connected in that case, not just for large n, but for all n. Where's my eraser? Oh, there it is. So, so in the interest of time, I think I will talk about, I have time to either talk about S5 extensions or about Pro2 extensions. I think I'm going to talk about Pro2 extensions because Nigel's here, and then Nigel can help me say anything I need to say about Pro2 groups. In some sense, the flavor of these two things is quite similar.
En dan nog heel interessant gelezen with hyperelliptic curve case. So there you would look at hyperelliptic plus an abelian covering.
Yeah, and that would be sort of that can be identified with the space of sort of multi-dihedral coverings of P1, and that's the identification. So, okay, let me move forward in my notes here. So now let me so Pro2 groups ramified at random primes. So again, let's take this question and sort of think of it over a function field instead of over a number field. So let's take U to be an open subset, actually, of the affine line over FQ. And it's actually going to be the affine line minus, minus 2 points. But actually, these will be defined over F Q to the D for some large D, because I want to sort of model spec Z with two large primes removed. And now we want to ask about, let's take, and then Q odd. We take G, a finite 2 group, and ask how many maps we expect to find from pi 1 of u to G. In other words, how many covers of this curve over this finite field by this finite group G do we expect? We expect to find. Well, let me translate this question in another way. And let me say,
On two maps.
say again?
On two maps.
Yeah, let's say surjective maps, and let's actually say we want this to we want these covers to be totally split at infinity. So we'll see how that works group theoretically in the diagram I'm about to write down. So let's say yielding covers split at this infinite place I've chosen in my well, I wrote A1, so I've implicitly chosen that.
Say minus 2 points, you have 2 closed points with residue field equal to?
Actually, it could be D1 and D2. They don't have to be the same residue field. But yeah.
Oh, but the residue fields are contained in. Oh, but you contain it, or D is not fixed. Or you just.
No, these are what are growing actually. I mean, I'm sort of the number of branch points, the number of points missing from U, geometrically is growing. But I'm.
So you just mean A1 minus 2 close points.
Yeah, A1 minus 2 close points.
Unspecified.
Of unspecified degree, but you should think of it as being very large. Because after all, when I say random, there has to be some set that's growing to be random over. So that's what it is.
If you want to think split at infinity, why did you remove infinity for the positive?
Only because I didn't want to then have to say, and my point that I'm removing is not.
That's natural base bound also infinity.
Yeah, and that's what I'll write down this, and you'll see the section I'm going to use is. So a way to think of what this set is so I have the usual exact sequence. And now, as you say, I'm going to have this. I choose I guess I have to use a tangential base point at infinity. It doesn't matter which one. I have a section going back. So base point at infinity. And the question I'm asking is really the same as, this is actually like in what Florian was saying, where you sort of want the kernel of this map is supposed to be a finite index subgroup which contains the image of this section. So what you're really looking for is homomorphisms from this big étale fundamental group modulo the subgroup generated by the image of this section to G. But another way to write this is if I look at the surjections from the geometric Galois group to G. You see, this is a thing that's much easier to study, right? Because this we know what it is. It's a profinite free group on some number of generators. So this is sort of something that we can just discuss quite easily from group theory alone. It's a k-tuple of elements of this finite group. But actually, to be precise, since I'm requiring that all the monodromy be of type C, I should put little c's up here to remind you that the distinguished generators of this group are forced to land in that conjugacy class in G. But now on this group, on this set rather, we have an action of the automorphism group of this geometric pi1 acting by composition on the left. And actually, we're looking precisely for the elements of this set which are fixed by the action of Frobenius through this section on the geometric Galois group. So now what I'm asking you is, I have some finite set which you can write down quite explicitly, and I have an action of something, and I want to know how many fixed points I expect. Well, this is again a question of monodromy. I mean, if you're willing to sort of say that things are random. So the point is that what is this automorphism of the geometric fundamental group? This is sort of, in some sense, the fundamental Anabelian question. So where this thing sits, thinking of it as, and now I'm going to be slightly lazy because I've chosen a section. I'm really going to put this in ought rather than out, because again, since I've done this rigidification, I'm not thinking of conjugacy classes of these things, but the homomorphisms themselves. This is in the automorphism group of the geometric pi1. but it actually sits inside a smaller group. It sits inside what Ihara calls the profinite braid group. So it sits inside Ihara's braid group, which is those automorphisms such that there exists some lambda in z hat star such that alpha of xi is equal to xi to the lambda for each of the classes of the punctures, the distinguished generators, xi. So this kind of definition in the discrete case would give you the braid group. That's why Ihara calls this the profinite braid group. This is where the Frobenius naturally lives. In fact, it even lives in a coset inside this group where lambda equals q. So, so I want to sort of suggest, or just outright say, that this is supposed to be analogous to the random matrix justification of the Cohen-Lenstra heuristics. Namely, so here's the little diagram. You should think of, I guess, GSP ZL is analogous to, this is on the abelian world, is analogous to Ihara's braid group. Here, Frobenius lies in this particular coset. And here, too, Frobenius lies in, maybe I'll call it braid group hat, although you have to remember it's not the profinite completion of the braid group. It's a different thing. But for now, I'll just call this braid upper Q. And then you can say to yourself, just as over here we said, well, maybe Frobenius is a random element of this profinite group. Here, too, you can say, well, what if Frobenius is a random braid? So if you like, let me kind of say something completely ridiculous for a minute. I mean, in some sense, the content of some Anabelian theorems, like the theorem of Tamagawa, is to say that at least these Frobenii kind of stay away from each other. That at least if you have two different curves, it's not going to be the case that Frobenius acts in exactly the same way on the geometric pi1 of the two curves. So that's some statement that that's some Anabelian statement that that the Frobenii don't collide in the automorphism group. So what I'm proposing here is actually what I'm sure it's a mistake to say this, but what you might call a kind of Anabelian equidistribution statement, where you say not only do these Frobenii not collide, in fact they kind of spread out all over this group. Now, if you sort of let Q go to infinity first, you could prove something like this. But I'm saying even some sort of more abstruse version of this, where Q is fixed, and as the number of branch points grows, these are larger and larger braid groups, and I'm saying that in some sense one expects Frobenii to act like random elements of these braid groups. Now, in what sense do I mean that? I mean that if Ihara's braid group acts transitively on this set, so the fundamental combinatorial question now is, so the combinatorial question is, does this profinite braid group, and certainly sitting inside here is the usual braid group, acts transitively on this thing, which is really no more than some number of copies of G. The answer being yes, you're asking what's the expected number of fixed points of a transitive action of a group on a set, and the answer is 1 by Burnside's lemma. So, and that turns out, now I'm sort of phrasing this in terms of, on the abelian side, I phrased something in terms of pretending an element was random in a matrix group, and then I showed you that the results that that heuristic gave were also produced by a statement of vanishing of cohomology of certain moduli spaces. So here too, what I'll say, but I won't say any more, I won't sort of prove anything more, but to say it, is that the heuristic you get from assuming that Frobenius is a random automorphism of this geometric pi1, that is a random braid, is exactly the prediction that you would get by predicting that these Hurwitz spaces indeed have vanishing cohomology. So predicting that, well, I've lost the statement now, but this statement for the, here it is. So they're predicting that this statement is true. And so, so I won't say anything about A5, only to say that, of course, we're really predicting a Poisson distribution hiding there, as you can guess from the form of the probability of getting 0. But I'll just say that what this allows us to do in the case of pro-p groups is to, so maybe I'll just close by making the statement about pro-p groups that you should expect. And I think I'll just state it for p odd just to make it, just because I'm at the end of my time. So, sorry, let me get the right page. So this leads us to predict that that if, let's say, if P, Q are random 1 mod L, L odd, then the probability that if I look at the maximal pro-L extension of Q unramified away from P and Q, the probability that this is isomorphic to some given L group G should be the number of pairs of conjugacy classes in G such that on the one hand, C1, C2 are generators for the abelianization, and both of these are, oh, and sorry, I should say, this is the case where G-ab is Z mod L Z squared, so 1 mod L, not 1 mod L squared. Then you want both of these conjugacy classes actually to be preserved by raising to the L plus 1 power. So this is some set of conjugacy classes divided by the size of the automorphism group of G. So here's our mass. Here's where we're counting things by mass rather than by numbers. Of course, what these conjugacy classes are supposed to be are the image of tame inertia. And in some sense, what we recover, this kind of non-abelian Cohen-Lenstra is saying that just as Cohen-Lenstra predict, I didn't say this, that the probability of a certain group appearing is proportional to 1 over the size of its automorphism group. An unramified Galois group like this comes with this extra data, these classes of tame inertia. And essentially what we're saying here is that if you ask not just what group do you get, but what group endowed with this structure of inertia conjugacy classes do you get, you indeed get each of those weighted by its automorphism, 1 over its automorphism group as a group with extra structure. So sorry I didn't get to talk about A5, but I'll stop there. Thanks. Yeah.
I just wanted to add that this checks in hundreds of cases. Because, I mean, you can explicitly test it.
Yeah, I should have said, so right, like, as for the real Cohen-Lenstra, there's lots of cases in which you can prove theoretically that this gives the right proportion, and lots more cases in which you can just run through tons of number fields and sort of see that it appears to be giving roughly the right proportion. So I mean, we've just started our numerical investigations, but so far it looks quite good.
How did you make a guess about infinite unramified?
So in Cohen-Lenstra, one sort of sanity check for that conjecture is you know that the group is finite. So if you add up the probabilities that they assign to every finite group, you better get 1. And you do. Here you don't. We can't prove this, to be honest. I mean, but I mean, it looks very strongly like the sum of this overall finite. Well, this is, I mean, the one we've really done work on is L equals 2, so you have to say something a little more complicated, but in the relevant case, you sum over all finite groups, and it looks like you're getting 15/16. And we sort of know where those 1/16 groups are hiding there. Sort of, we think every infinite group should have probability 0, but all the infinite groups you get seem to look kind of the same in the sense that if you look at the size of group mod kth term of lower central series, that gives you a sequence of integers. It's the same for all those groups. And sometimes I think they have the same Lie algebra or something. I don't quite know how to phrase this correctly, but they somehow are in some, they're all cousins to each other, all these infinite groups that arise, the ones that arise 1/16 of the time.
What are the kind of necessary conditions for this group G, like in terms of generators and relations? And,
Well, it should be pretty general. I mean, our vanishing conjecture, I didn't say it, but it's really, it's not just a conjecture about cohomology. We actually have a conjecture sort of, you can actually, I mean, this is why we have a homotopy theorist on board. I mean, that's who Westerlund is. As algebraic geometers, it's sort of hard to stick these Hurwitz spaces together. Maybe one sits in the boundary of the next or something like that, but it's rather complicated. But the homotopy theorists can just glue things together however they want. And so it actually makes sense for them to talk about the Hurwitz space with infinitely many branch points and say, like, what space is this? So we have a conjecture explicitly that it's a double loop space of a certain space that we can write down. It's supposed to be true for any finite group G. It's very much in conformity with the kind of philosophy of Madsen, Weiss, Tillman, et cetera, et cetera. So
it doesn't have to be balanced or whatever.
oh, so for I'm sorry, for this.
For G, yeah.
I'm sorry, I attributed your question to the wrong slide.
No, that's
Yeah, so for this, yes, I should have said this. This statement holds for balanced groups, and sort of the reason for that is that really what this method is good at guessing is the number of surjections. But actually, if G is balanced, so correct me if I say something wrong, but if G is balanced, if you have a surjection from this group to here, it has to be an isomorphism. And so the number of surjections is actually just, you divide that by automorphism in the group of G, and you get the probability that it is isomorphic to that group.
What's this balance?
The same, H1 equals H2. Yeah. So yeah, in that case, you have this very wonderful feature, which is why I don't make a general prediction for general finite groups, that counting the expected number of surjections onto G is the exact same thing as computing the probability of being isomorphic to G. You just divide by the automorphism group.
it's just nice, but it doesn't, maybe it's not balanced.
So for non-balanced groups, I would say I would be able to sort of make a prediction. This would predict the the expected number of surjections, the expected number of G extensions unramified at P and Q, except for the fact that in that case, we know this transitivity. For the balanced case, we can prove the transitivity, and I don't quite know how to prove it. I'm not even sure if it's true, so I'm a little hesitant about the non-balanced case, because this is, just as it's actually not a trivial fact that the moduli of hyperelliptic curves, the monodromy in the symplectic group is full. I mean, it is a fact, we know it, but I mean, you got to prove it. It's a real, it has content to it. So too, all statements like that have some content, and you have to, at some point, buckle down and prove them. So we proved it for G balanced, but not in general.
And for more than 2 primes. Right? For any number.
Oh yeah, I'm sorry. So in the interest of time, I mean, the conjecture is certainly more general than this. It's for an arbitrary L, including L equals 2, for arbitrary number of primes, et cetera, et cetera. I mean, this kind of case is the case where so far we've done a lot of numerical tests, but I mean, one can conjecture whatever one wants. I mean, yeah.
So in the case of elementary L group, you proved a certain stability theorem for the cohomology of the complex space, complex Hurwitz spaces. And what is the point, rough point of the proof of this stability?
So I mean, I said this very quickly, but it is essentially, as you say, a statement about the cohomology of complex Hurwitz spaces. And the idea, I mean, these are k-pi1s for certain finite index subgroups of the braid group. And in a sense, what you want to do, and it's just what Hara does for the mapping class group, is you want to find some nice complex on which that group acts. And in fact, it's the same complex as, or I mean, it's not quite the curve complex that Hara uses because he's doing MG, but it's the arc complex, which pertains to the braid group. So you have some nice complex in which the braid group acts, and then you go to other people, not us, to make sure that that complex has no homotopy groups except in quite high dimension. It's approximately contractible in some sense. So this is the theorem of Hatcher and Wahl. Now what have you got? You've got some very combinatorially defined complex, which you can describe your group action on very explicitly, and it all has to do with actions of braid groups on these kinds of sets. And what you know is that from a homotopical point of view, that complex is approximately a point. So you can use a spectral sequence to compute that the cohomology groups of that complex mod the fundamental group of Hurwitz space, and then because that complex is approximately a point, what you're computing is essentially the same as point mod Hurwitz space, which is to say point mod fundamental group, which is to say you're essentially computing the cohomology of the space because that space is a k-pi1. So so that's what it's like. That's what it's like. And in the end,
So in order to treat the combinatorial property of this group action, you need to require the extra assumption on the fact that the group is elementary Abelian. So for general G, so it is difficult. So which part is?
So I'll tell you, I can say what's difficult about it. What's difficult is the following super annoying fact. You see, when you do the spectral sequence, I've said everything here in order to sort of sound more classical and to reduce indexing. I've said everything in terms of onto maps from fundamental groups to G. From the point of view of the proof, that's not natural. It's natural to consider the connected and disconnected covers together, and your Hurwitz space just means every map of the fundamental group to G, every G cover, whether it's connected or not, et cetera, et cetera, et cetera. So the problem you have is that, as you say, everything comes down to the combinatorics of this action, which is to say the combinatorics of the components of the Hurwitz space, the H0, right? In a spectral sequence, you're always doing induction down in dimension. In the end, all the combinatorial brutality is located in the H0, and if you can handle that, then you win. Here's the problem. And then I won't belabor it, because I know I'll just say this one thing, and then we can break. So let's say what happens for S4, okay? Let's say G equals S4, and C is a transposition. And you're studying the components of this space. Well, now, among these covers are the ones where the image is not the full S4, but is only, let's say, a Klein 4 group, right? Or actually a group, well, a Z mod 2Z cross Z mod 2Z. So inside here, you'll have space of covers where image of pi 1 in G is like the group generated by these two flips. And now the problem is this thing that was like one conjugacy class here, in this group it splits up into two conjugacy classes. And so if you study, and now if you sort of say, okay, I have n branch points, now all of a sudden this space has more components, because you have to say how many of the n are in this conjugacy class in this subgroup, and how many of the n are in this conjugacy class. So actually, if you look at this full space that carries the disconnected covers too, even if you start with only one conjugacy class, sadly enough, as n grows, the number of components doesn't stabilize. So literally, the statement is false. I mean, even the H0 doesn't stabilize. So this is very annoying. And unfortunately, this seems like a completely stupid problem that you could get around somehow. But we don't see how, because in the spectral sequence, in the induction, you don't get to strip out the disconnected ones. They're there, and this kind of horrible H2 has the perfect right to kind of percolate into the H1 and the H2 and everywhere, and we don't know how to control it. So we need this very funny condition on G that the conjugacy class has the property that in the intersection of the conjugacy class with any proper subgroup either stays one conjugacy class or it's empty. Now that, unfortunately, is very hard to satisfy. But fortunately, it's true for dihedral and multidihedral groups. I actually don't, it's some question of finite groups. You can sort of by force construct other examples. I don't know if I know other interesting examples. And so that's a serious technical problem that we don't know how to get around. I would say that...
Well, that forces every abelian subgroup to be cyclic. You have that condition which tells
Well, that's not true, because it's true for Z mod LZ to the R semi-direct Z mod 2Z. Like the class of involution still has that property in that group.
Oh, just for involution.
Oh yeah, so I mean, it's a property of the group and the conjugacy class. Yeah, oh yeah. If it had to be true for every conjugacy class, you would be very, very sad. No, it just has to be true for the conjugacy class that you're studying. So I think, to be honest, I think this is a situation where the only way to get around this is to prove a new statement about there would be some kind of complex you could make that's a modification of the R complex that would sort of, you could strip out the non-connected covers at that level and then try to prove that that complex sort of is homotopically trivial in a range of degrees. But to be honest, that's the part of the proof that we take off the shelf and don't know how to do. I mean, we sort of take the theorem of Hatcher and Wall, and it's neatly packaged for us, and there it is. So to prove a new theorem of that kind, I think, I guess I would be delighted if that weren't necessary. If it is necessary, I'm happy to work hard on it, but I don't have confidence that I know how to do it. Because that's even farther from number theory than this.